So this video is going to be split in two. I apologize. Okay, the Rydberg constant, the energy, basically what we're saying is the energy can be expressed as the Rydberg constant times z squared over n squared. Okay? So the infinite central mass is the constants that come out in front here, depending upon how you arrange the constants, right? And so, again, I love the Rydberg constants, half the electron mass, rest mass of the electron times alpha squared. Do you ever have to remember all the nasty constants that go into it again? No. Half the rest mass of the electron times alpha squared. From there on, what's the rest mass of the electron? 0.511 MeV divided by 2. This is basically 1 over 137. Square it. You can do it with your iPhone. Boom, you've got a rough value for the Rydberg constant. It's pretty awesome. Anyway, when you plug in these numbers to the highest precision, you get about 2.17 erg, 10 minus 11 ergs, or 13.6057 eV. Okay, this is the quoted value from NIST at this stage. Okay. Now, that's for an infinite nucleus, where the reduced mass equals the electron mass, so this ratio has gone away. Okay. In general, for hydrogen, basically, for what I'm going to call a hydrogenic atom with nuclear charge, Ze. Now I'm going to define for you hydrogenic atom. That is any atom which there's only one electron orbiting the nucleus. Hydrogen is a hydrogenic atom. Singly ionized helium only has one electron. It is a hydrogenic atom. Twice ionized lithium, 2 electrons removed, 1 electron orbiting, is a hydrogenic atom. Okay? So it can be an ionic state of a metal as long as there's only 1 electron. Then it behaves like a hydrogen. All its structure will end up being exactly like hydrogen, except for you have to account for the charge. So nuclear charge Z, which is, everybody knows Z, the number of protons, times the electric charge. So for a general hydrogen atom, what I'm calling R sub Z, it's equal to Z squared times the ratio of the reduced mass to the electron mass times the R for an infinite nucleus. Okay? Everybody got that? The Z here. Okay. And then, so here, this is of a charge just Z equals 1. Okay. Now we're just putting Z in here. So here's Z squared, and then the ratio. So anyway, this number is the true number for hydrogen, where Z equals 1. Basically, you have to take the R for the infinite, multiplied by the ratio of the reduced mass to the electron mass, which is 0.99946. Z is 1 for hydrogen, and you get the actual true Rydberg constant for hydrogen. And notice that it is not 13.6. Now, approximately it is, but it's not. Okay. The actual Rydberg constant for hydrogen, when you account for the reduced mass of the electron, is 13.59843 eV. And that matters. Okay? That matters. This is the basis number for all the energy levels, so that number matters. So the energy now can simply be written for state n as R sub Z over n squared minus sign. Very simple. Okay? 13.598 eV divided by n squared. You now have the energy structure of hydrogen in eV. Okay? All right. Any questions? Maybe that's presented a little differently than you've seen it. I'm not sure. Now let's talk about introducing a lot of definitions. And these definitions you've heard of before, but I just want to define them. Definitions for various different types of energies. And even though I know that most of you are sitting and go, I've heard of this before, you know, it's amazing how it still will trick you up when I ask you on the test, or if I ask you at your class orals. In other words, they start to get a little jumbled in your head, and then you lose your confidence on what's what. So, but I'm going to be using these terms throughout the class, and so it's very important. And you're going to be making calculations using these different energy structures to get the ionization balance of, say, iron or helium in a gas. You have to know these different energy levels, and when you program them up, for your computer modeling of the gas. And so, it's amazing what you start programming, and then you start scratching your head. Maybe I didn't. Happened to me all the time. Still happens to me all the time. I think I understand something. I start to actually work with it, and then I find out that I really only had it at the 80% level. All right. First one is transition energy. That one's pretty obvious. That's the energy between the upper state and the lower state. And I'm going to introduce my notation. Okay, so, okay, all right. So, blah, 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 blah. Sorry, I'm trying to figure out to make sure I get it right. Right. We will always use primes for upper states. So this will be N prime and this will be N. Okay? And when I talk about a transition like this, we're going from N to N prime. So the energy associated with this would be AN to N prime. It's almost as if there's a little up arrow there for the transition. And when we talk about a transition that goes down, we're going to call that E N prime N. And it's really important you get that down. Okay? The bottom subscript is the initial state, and the top script is the upper state. That is going to be the convention that we are going to adopt. It's very critical that that gets lodged into your brain. Okay? All right. So the energy of the photon that comes, this energy level here is just going to be called E sub n, and this energy level here is going to be E n sub prime. Single subscript, single level, two subscript, superscript, transition energy. Okay? So, N prime, E n prime, N, E n, absorption, N to N prime, initial state N to N prime, emission, N prime to N. Okay. The energy of the photon, gamma, whether it's an absorption or whether it's an emission, is E sub n minus E sub n prime. That's pretty obvious. There are different ways to write that. Okay. H times nu, or HC over lambda. Again, now I'm also going to use the notation on the frequencies and the wavelengths for bound-bound transitions to have a subscript and a superscript, where the initial state is the lower subscript and the final state is the upper subscript. And what I'm saying here is this is completely symmetric up and down. That the energy of the photon, whether it's being an absorbed photon or whether it's an emitted photon, they're identical. Okay? That is called the transition energy. This is how we've defined the transition energy. N to N prime or N prime to N. Now, if you have the special case, so when you take the definitions of E sub n and E sub n prime, okay, they're symmetric. It's basically, you've seen this formula before, it's the Bohr formula, Rydberg constants times 1 over n prime squared minus 1 over n squared. Because each one of these, this is equal to minus RH over n prime squared and this one is equal to minus RH over N squared. So when you take the difference of those two, that's what you get. And I know everybody's seen this, so this is review. Transition energy. Let's talk about something called the excitation energy and or potential. This is a key concept because this tells us how much energy is required to lift a ground state electron to an excited state. It's basically the energy difference from the ground state to the excited state, but it tells us how much energy is required to get us up there. So it's called the excitation energy. Okay? Quite clearly, that's E sub n, if you're going to excite up to state n from state 1, is 1 minus 1 over n squared. Okay? We will use the notation of chi. If you happen to go and look at the book Gray, Stellar Atmospheres, he'll use a chi. It's a very common notation for the excitation energy. Basically, it's the same thing as a transition energy in concept, except it's from the n equals 1 state. And it's telling you, again, how much energy it takes to get you excited into state n above state 1. Okay? All right. Right. Note the excitation energy of the ground state is always 0. Okay? Why is the ground state excitation energy always 0? You're standing on the floor, people. If you're already in the ground state, it takes 0 energy for you to stay in the ground state. It's defined as 0. Okay? Because state n is n equals 1, so to go from state n equals 1 to state equals n equals 1, if you subtract e sub 1 minus e sub 1, you get 0. I mean, it doesn't take any energy. So the ground state excitation energy is always 0. That's a mantra. It's amazing how that confuses people down the road. Okay? If you're an electron, whether you're in a multi-electron atom or you're in hydrogen and n equals 1 state, if you are the last outer shell electron and you are in the ground state, your excitation energy is 0. You are at the floor for you. The excitation energy then is how much does it take to lift that ground state electron up to another excited state. Okay? Then we have the excitation potential as well, and that is basically the differences between two states n and n prime. In other words, it's an energy and it's a potential. Once you're up there, you have a certain amount of potential energy. That potential energy is going to be equal to what the excitation energy was. Okay. Ionization energy. So you've had 3: transition energy, excitation energy, now ionization energy. That's pretty obvious. That is going from state n, wherever that is, to infinity. Okay. What's the energy at n equals infinity? Well, the energy of state infinity is equal to minus r sub h over infinity squared. 0. Okay. Below that, it's negative. You're bound. But to get you up to 0 energy, just unbound, okay, well, that's going to be easy. E from state n to infinity, okay, that's a capital I for ionization. Okay, I know you can't see it there, but it says subscript capital I denotes ionization. So from state n to ionization, the I for ionization is E sub infinity, which is 0. State n minus that is minus, so the result is minus of E sub n, but that's just positive RZ over n squared. So the energy required to ionize the atom from state n is just R, the Rydberg constant, divided by n squared. Okay? That's supposed to be an H. Yep. Well, no, I'm doing it, that's not supposed to be an H. I'm doing it in general for any general atom, right? I'm doing it for hydrogenic atoms. Could be helium that's got one electron. All right. Whoops. Any questions? So, following that through, given that the energy of the photon is equal to h nu or hc over lambda, okay, you can solve for the fact that any photon with energy greater than the ionization energy can effectively ionize the atom. That limits us to frequencies in the range of r over h n squared, or wavelengths less than hc n squared over r. That's just simple math, okay? The fact that E n sub I is equal to r over n squared, okay? And then you've got hc over lambda is greater than r over n squared. Hc over lambda is greater than or equal to r over n squared. Or you have h nu is less than, sorry.
Is that for hydrogen?
Except for hydrogen.
This is for hydrogen, right? Wouldn't there be a factor of Z?
For hydrogenic atoms only.
That's where the Z is.
So that's why the Z, because I'm allowing for it to be either Z equals 2, or Z equals 4, or Z equals, right? Does that answer your question?
Yeah.
Yeah. So I want to remind you that all this very simple stuff is not the way that the other atoms behave. I'm going to teach you how the other atoms behave, but we're going to start with hydrogen because it's or hydrogenic atoms because they're the simplest. So basically, those two equations come from those relationships. Do you remember that if you have a photon that has energy higher than what it takes to ionize it, the ionization energy, which is R sub Z over n squared, from n squared from state n. If you have photons with higher energy than that, they also can ionize it. So this is the range of frequencies and the range of wavelengths that can ionize hydrogenic atoms. Okay. All right. Then we have what's called the ground state ionization potential. And this is basically defined as also E infinity minus E1 or equal to RZ. Okay? So basically, that's telling you, remember the potential energy was how much energy it takes to get you from the ground state to state n. This is to get you from the ground state to infinity. The ionization potential. We have the excitation potential or excitation energy. This is the ionization potential or the ionization energy. It's the same thing. It's just to take you to infinity, n equals infinity, instead of some finite n from the ground state. Okay. So basically, it takes a photon of energy equal to the Rydberg to ionize the ground state of a hydrogenic atom. That should make sense when you say it that way. So what I did was I put these all together. Here's your one-stop shop, Walmart, for your energies. You got your energy minus R sub Z over n squared. You have your transition energy from initial state to final state. That's R sub Z 1 over n prime squared minus 1 over n squared. You have your excitation potential. That is chi of n, which is RZ 1 minus 1 over n squared. Okay, because you're going from the ground state to state n, and then ionization energy, RZ over n squared, energy required to ionize you to n equals infinity from state n, and ionization potential, which is just the Rydberg, which is basically the energy required to ionize you from the ground state. So basically, N is 1 for hydrogenic atoms. Any questions? To which I always get nothing. I get crickets. Except I'm too deaf to hear crickets. Okay, you've seen this before. This sometimes is called an energy diagram, sometimes called a Grotrian diagram. I'm just going to call them Grotrian diagrams after the German physicists who first developed them. Okay. This diagram is worth a great deal of study. Why do I say that? Because the left-hand panel is hydrogen, and the right-hand panel is the hydrogenic atom / ion of helium. And you will notice something about them. They look freaking identical, except the energy scales. Because they are. They only scale by what?
The fine structure coefficient? The fine structure coefficient?
No, we're not to find structure yet. They only differ by the charge of the nucleus. Oh, did I simplified it. But they only change by the charge of the nucleus. For example, the ground state energy is minus 13.598. Okay? Multiply it by 2 squared, which is the charge of the helium nucleus, and you get minus 54.418. So the electron bound to the helium, hydrogenic helium, the one electron, is bound at minus 54 eV very tightly, whereas the one around around a hydrogen nucleus is bound only at minus 13 and some change, 0.598, 0.598, 0.598. Okay, so the difference there is the charge of the the protons in the nucleus. And then if you look at the entire energy scale, here it goes, minus 13, minus 12, minus 11, being bound. These are bound energies, the energy E sub n. They're all negative, bound energies. This is chi, the ionization energy or potential. Notice that it is 0 in the ground state and goes positive up to exactly, at n equals infinity, 13.598. This goes from 0 to 13.598. This goes from 0 to minus 13.598. They're exactly flipped. The n equals 1 state is bound at minus 13.598, has excitation energy of 0. N equals 2 is bound at minus 13.4 eV and has an excitation potential of 10.2. It takes 10.2 eV to get you up there. Okay? But when you're there, you're bound at minus 3.4. Go to helium, same thing. Ground is at minus 54. 2 squared times that, minus 13.6. Wow, that's kind of interesting. That's very close to that number, isn't it? That's going to cause some issues later on. Okay. Minus 6. 40 eV to get up to the second state. That's a lot of energy. That's a strong photon. That's a UV photon. 48, 51, 52. From 0 positive, from negative 54 positive. All right. Now, I lied a little bit. It's not only the charge of the nucleus, the Z quantity squared, that has made this energy scale different than that energy scale. There's a small additional factor. When you have 2 protons and 2 neutrons, you have more mass than just 1 proton. So the electron going around the hydrogen has a reduced mass correction that's very small, whereas the electron correction for the reduced mass is around helium is different. So not only do you have the factor of z squared, but you also have the correction factor for, which is on the order of 0.999. It's very close to 1. But I just have to mention it. You do have the correction factor for the mass correction of the nucleus as well. Okay? But other than that, you can see that these are extremely parallel. And then the transitions, we know we have the Lyman series, 2 to 1, 3 to 1, beta, gamma, 4 to 1, delta, 5 to 1. Okay? And then we have the limit to ionization, which has a wavelength of 912. We have H alpha, okay, 65, 63 from 3 to 2, H beta, 55, 45, 51, etc., etc. And here's one thing I want you to realize about this Bohr model. Only one exact energy difference. There's no fine structure. In the Bohr model, you get 65, 63 when the electron drops down from here. You get 65, 63 angstrom photon. One photon, infinite spectral resolution, Gossamer thin, exactly at that wavelength. We're going to find out that that's not the case. And we're going to find out that these energies aren't exactly right. Okay, we're going to find that out. Any questions about this? All right, so here are some spectra to look at. On the top we have H0, meaning neutral hydrogen. Okay. This is the Balmer series. Your H alpha at 65, 63, your H beta, gamma, delta, epsilon, and then you get the Balmer convergence, and then you get the ionization edge here, which is where the Balmer decrement will occur. All these photons have wavelengths greater than hc n squared over r sub z. Let's look at the Lyman series. Now we're down in the ultraviolet, 1600 down to 200. It's a very much narrower range of spectrum, and I'm not sure that's always usually appreciated. Okay, this is over 6600 to 3600. This is from 1200 to about 912. Okay, 1215. Lyman alpha, Lyman beta 1025, gamma 975, blah blah blah, the Lyman convergence, and then the Lyman break. Okay. Now let's look at the so-called Lyman series and Balmer series of the hydrogenic atom of helium with one electron. Here's the n equals 2 Balmer series. All the way out here in the UV, beta's at 1215. It's almost at the exact same wavelength as Lyman alpha. Oh! Why doesn't that cause problems in the universe? We go around measuring Lyman alpha absorption in quasar spectra all the time. And we never scratch our heads and go, I wonder how much of the Balmer series HE beta, if you will, line is contaminating my Lyman alpha line. How come we don't go around worrying about that? Yes?
It's a much higher energy for the helium line, so it's probably dominated by the lower ionization.
I'm not sure I'm following you, Drew.
Yeah.
You're saying the right words, right?
Singly ionized helium that is then excited is much less common than neutral hydrogen.
Bingo. That's what you're trying to say. Yeah.
That's what he was saying.
That's what he was saying. I was just holding your feet to the fire, make sure that, because I'm a scientist, I'm that way. And if it was on a test or oral test, I'd have to be like, wait, can you say that another way, Drew? Right. But you had all the words there. If you're a gas cloud out in intergalactic space, your hydrogen is mostly in the ground state, n equals 1. You're going to mostly make your neutral Lyman alpha lines. because your electrons are all sitting down there, just waiting to be excited. But first you got to be in some kind of hot gas that's going to ionize helium, and then you have to have the leftover electron that's sucked down at minus 54 eV get all the way excited up to, what was it? Excitation energy was 40 eV. That's a lot of energy to have around to get most of your ionized helium electrons so they're sitting in the n equals 2 state, so that a 1215 angstrom photon that happens to come by will end up exciting you to the next state. Okay? It's not going to happen. If you are in a gas where you have ionized your helium once, I guarantee you, you've ionized your hydrogen. You're not going to even see Lyman alpha. That's why we don't bother with it. Okay? Really important to think about these things. You know? Just because you see that these lines line up the same in the universe atomically does not mean that you're going to have to be worried about the contributions. Or if you see some absorption at this wavelength, probabilities are 99.9999999%, it's Lyman alpha. And if it's not, you're going to see some other indications in the spectrum that you've gone through some very, very hot gas, in which case you won't see any signs of any other hydrogen at all. Okay. But the delta is here with the beta, okay? And the edges are nearly the same. We never see ionization edges due to ionized helium in spectra. Really don't. It takes a lot of energy. And then you have the Lyman series all the way down here in the 200s to 300s, alpha, beta, and whatnot. Okay. So way more UV than the Lyman series. Okay? Are you ready to switch gears? Okay, we're going to go from this classic model of the angular momentum being some interval of NH bar to a whole different ballgame. Okay. So it's going to be a quick review of the Schrodinger atom on the order of the review of the Bohr atom. Okay. Now, it all started in 24 with a hypothesis from a guy named de Broglie. This is his PhD thesis. Talk about your one-page PhD thesis. Okay, but it was a brilliant insight. Okay, the wave duality, particle duality. Okay, you've got some mass moving at some velocity, divide that into h, and you get its equivalent wavelength. Okay, particle duality. And it turns out, though I'm not going to go through it, this paragraph shows you how you instantly, from this relationship, can come up with the same equation we got for Bohr. And therefore, the same exact result of the Bohr atom. In other words, you can equate the stationary states of the hydrogen atom to the fact that it has to be an integer number of wavelengths around the circumference of the orbit. If you think about that, that's so that it constructively interferes. You bring the orbit radius down a little bit, it's not an integer number of wavelengths, and so it would destructively interfere. So the electron has to only exist and persist in that narrow region where it constructively interferes with itself. It's a beautiful, beautiful, beautiful argument. But in the end, that drove Erwin Schrodinger, to propose that we should not handle these subatomic particles as particles, but as waves. And everybody knew the standard wave equation, so he plugged in the electromagnetic potential and the kinetic energy of the electron, okay, into what's called the Hamiltonian, and cranked it through the wave equation. Okay, so this is the expression for the kinetic energy and the potential energy in general terms. Okay, this is a spatial operator which gives you the second derivative in the x, y, and z directions. Okay, and from that you can do this in spherical coordinates, blah, 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 blah. And you get a special relationship. You get basically spatial dependent but time independent solutions for where the electron is going to be, and you get a time relationship of oscillation of the wave, the frequency of oscillation of that wave, which depends upon the energy, the Bohr energy, basically. Okay. So this is basically an oscillatory function, right? Because that's equal to the cosine of En over h bar t plus I sine. Okay, this is an oscillatory function in the complex plane. So this is an oscillation of the wave. This is its amplitude at radius r, and it's basically saying that at any position you have the amplitude of the electron waving up and down. That's at some r. A wave. Okay. So anyway, when you take the Hamiltonian and operate it onto, say, the spatial component, there's the Hamiltonian. You're taking the second derivative spatially, multiplying it by the potential. You're summing the two together of the wave function. It turns out that when you take that operation on this wave function, you get the energy of the state times the wave function back. That was the beautiful thing of the wave equation. So, now and again, we will also use the notation omega sub n for the angular frequency, which is basically the energy of the state divided by h bar. Okay. This is a relationship that we're going to use a lot. Without this relationship, you can't understand atomic transitions and atomic physics, why certain transitions exist and why other ones don't. You've probably heard of permitted transitions and selection rules and forbidden transitions. That relationship right there is the mathematical toolwork for determining what transitions are which. And I will define those transitions later. Anyway, this is the Dirac notation, Bra and Ket. Basically, wave function of state n, wave function of n prime and state n is a spatial integral. This integral here means that it's basically over 2 pi over phi and 1 and over pi over theta. That notation is defined as. Okay. d phi d theta. Okay. That's what that notation means. You're just, and then this is over r equals infinity. So you're basically saying over all space, you integrate the product of the two wave functions over all space. Okay. Basically, this is a delta function, so that when n equals n, you get a 1 back, and when n prime does not equal n, you get 0. Okay. And that is defined right here. Dirac delta function is equal to 1 when n prime equals n, and equal to 0 when n prime is not equal to n. Okay. So that tells you that when you integrate the same wave function with itself over all space, you get unity. And when you integrate a wave function of state n and state n prime, you get 0 over all space. They cancel each other out perfectly. Okay. And this is going to be key. So you come up with something called the Bohr postulate, which says the square of the wave function provides the probability of finding the electron at r at time t within the volume element dv. Okay, the probability of finding the electron at r at time t in volume dv is basically equal to the product of the complex conjugate of n times n dV. So basically, the square of the wave function gives you the probability of the location of the electron. You probably heard that before. Okay. So, I think we have about 5 more minutes, so I'm just going to talk to you about the wave function a little bit. And then we'll get into the transitions. All right. So the wave function is now broken into 2 parts, a spatial part and an angular part. You've probably seen this before. The angular part is a function of 2 quantum numbers, n and l, and the angular part is a function of 2 quantum numbers, l and m. The whole wave function now has 3 quantum numbers, n, l, and m. It's over alpha, theta, r, theta, and phi. Okay. The relationship between n and the radial quantum number is given by this, and this turns out to be very important. N sub r is a quantum number that we really never use. We always use n as the principal quantum number, but that's equal to actually the radial quantum number plus L plus 1. Okay? And N sub r itself can go from 0 to infinity. All right? All right. So if we have, we know that L is a maximum when nr equals 0. Why do we know that? If this is 0, L is equal to n minus 1. Okay? And since the minimum of n is n equals 1, okay, and nr is always less than n, nr has to be less than n if you look at this equation, okay, because even if L is 0, nr plus 1, so nr is less than n. When you combine the fact that the minimum value of n is 1 and nr is less than n, you get the minimum value that of L is equal to 0. You can probably see that, right? Because this is 1, that's 0, and then this becomes 0 to make that equal to 1. Okay. So that tells you the range of L is between 0 and n minus 1. That's why I like to show this equation. All right. So we have L ranges from 0 to n minus 1. Okay. M is the polar projection, and it can go from minus L to L in states of increment up by 1. All right. So basically, what you should consider these numbers to be are the number of nodes in the wave. Okay, you're going around in phi, and if m equals 5, it tells you there are 5 nodes in the wave. If m equals 10, there's 10 nodes. Okay? L is the number of nodes in the polar direction. If it's 0, there's only one antinode, I should say. Okay. And then, or there's no antinode. And then if n equals 1, there's one antinode. And if n equals 2, there's 2 antinodes. Like that. So it basically, this tells you the geometry of that wave. Is that making sense? And so we can show some pictures now. First we'll show this relation, then I'll show the pictures, and then we'll call it a day. So here's the principal quantum number, 1, 2, and 3. Here's the angular momentum number, which is the number of nodes in the polar direction, 0 to n minus 1. So when n equals 1, it's only 0. Okay. When n equals 2, it's 0 and 1. When it's 3, it's 0, 1, 2. And then for what's called the magnetic one, which is the number of nodes in the azimuthal direction, it can go from minus L to plus L, because they can oscillate this way or they can oscillate that way. And so when L equals 0, it's 0. When L equals for 2, L can be 0 or 1. When it's 0, there can only be one node in the azimuthal direction. When L equals 1, there can be 3 nodes, a plus node, a minus node, or a polar node for the magnetic number. And you can see how this works. 0, 0, 1, minus, plus 1, minus, blah, blah, 2, plus 1, blah, 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 blah. So I'm going to stop there, and when we come back, I'm going to talk a little bit about those radial nodes, and then I'm going to talk a little bit about those polar and azimuthal nodes, just to give you a physical view of it, and then we'll talk about the energy structure. And from the energy structure, we'll get the transition structure. We're going to find out, punchline, spoiler alert, the energy structure of the Schrödinger atom is identical to the energy structure of the Bohr atom. It has no electron spin. That'll take direct. Okay. We'll see you guys on Tuesday. If you have any questions about the homework over the weekend, email me, Facebook, Canvas message, whatever. And, yeah. We'll see you guys around.